Okay, so for this one, we have this ice skater is going to hit this log or whatever this is, this beam, and going to grab on, and they're going to kind of start rotating and sliding at the same time, and it's frictionless. So is linear momentum, what happens to linear momentum? Well, there's no external forces, there's no friction or anything, so constant. Angular momentum, well, there's no external torques, so constant. How fast does the center of mass move? Well, that's related to the linear momentum. So that would be the mass of the man times the velocity of the man. And afterwards, it's going to be the mass of the center mass, so the whole system, times the velocity of the center mass. So this would be 70 times 18 equals, this whole mass here would be 70 plus 230, 70 plus 230, which is 300. And so we can solve for the velocity of the center mass. Okay, this is the first hard one. Okay, so okay. To the beams in the middle, where's the center mass? Okay. All right, so we're going to set our origin right here. So to figure out the center mass, I'm going to do it in the y direction. It's going to be the mass of the whole thing, 230, times its position, which is 0, plus 70 times the position of the man here on the end. So if this is 2.7, then this would be what, 1.35 divided by 300. So that's going to give us the center mass, and it's going to tell us how far it is from the center. Yeah, all right, so that'll be our answer. Okay, so Li must be equal to Lf, and for Li it would be for the mass, it would be mr squared for the man, times omega I, which is vi over r, equals, afterwards, it's going to be I of the man plus I of the board times omega f. Okay, this mr squared is given for the person to be 75, and it would be the same over here, 75, and it gives us I of the board as well. We know the initial velocity of the person, but this is the r is the thing we have to be careful of. So we just found the center of mass. We found this distance down to here. So let's say that's where the center of mass is. R is going to be from here to here. That's what R is. So the entire distance is 1.35. So if I subtract out the YCM from 1.35, I'll get R. So that's what R is. So R equals YCM. Yeah, I did it wrong. 1.35 minus YCM. Okay. Okay, so Li equals Lf because it says no angular momentum is lost. So this would be I times 30 days. So omega here would be 2 pi over 30 days, but this has to be in seconds, so 30 days have to be put in seconds. Okay, equals this is what I is for the future. So I future, I now, and this is going to be, what will be there? What will the period rate be? Way dwarf. Okay, so 2 pi over t, and this is what we're trying to find, the period in the future. So we want to know how long it takes for it to go around. Okay. All right, so we want to find the change in kinetic energy. So that would be 1/2 I in the future times omega final squared. So this right here, that's omega final, by the way. Okay, minus 1/2 I now times omega initial squared, and this right here is omega initial, and I'll let you think about what that last one is there. Okay. Okay, fix the midpoint. Okay, so if I want to figure out the speed here, this could be conservation of momentum. Pi equals Pf. Initially, this has got the Pi. We know what the mass is. We know, here's the mass. We know what the velocity is. And so then afterwards, they're stuck together. And so we know what the total mass is, 0.2, 0.2, 0.3. And you could figure out what that new speed is then. Determine the change in kinetic energy. So 1/2 the whole mass, I'll use big M, so that'd be 0.2 plus 0.2 plus 0.3 times that final speed squared that you just found, minus 1/2 the mass of this one, so VI squared. And so you can figure out the change in energy. Again, that's going to be negative, so you want absolute value. Okay, for the first part here, that's going to be finding the center of mass, and it wants to know from the left end, so this is going to be our origin there. So let's say 1, 2, 3. So center of mass would be the mass of 1 times 0 plus the mass of 2 times the distance away, which it tells us how long that is. So we know that distance, I'll say x, plus the mass of 3, which we know, times x as well, divided by the sum of the masses. And so you can figure out what that distance is, or that amount. For this one right here, the speed of the center of the mass has to be the same momentum conservation. So using mi pi equals pf, where this is the mass of the center of mass and this is the velocity of the center of mass, you should be able to figure out what the velocity of the center of mass is pretty easily. Okay, so for 3, to figure out what I is going to be equal to the sum of mr squared. So you found the center of mass a little bit ago, so let's say the center of mass is somewhere in here. So you could do this mass times the distance away squared plus this mass times the distance away. Now realize the whole thing's 0.5, so if you know this distance, subtract that from, oops, sorry. So if you know this distance, subtract 0.5 minus this distance to give you this distance. So this mass times this distance squared. And then finally this mass times the same distance squared. Sum all those up, and that'll be I. Oh, wait a second. Sorry. That would be the I after the collision. Sorry. That's actually IV that I just explained. Rotational inertia of the system immediately before the collision. So 1, 2, 3. Oh, I have the moving mass. So it's only good. Okay, sorry. So for I, that it just says for the moving mass, that's going to be equal to mr squared times v over r, because that's omega. The r's cancel, and so we get mrv. R is going to be this distance here, so it's going to be, sorry, this distance here. So we have to do 0.5 minus this that we found earlier, and that's going to be the R. We know the mass, we know the velocity. All right. All right, 5. Determine the speed of the system immediately after the collision. That's going to be conservation of angular momentum. So Li equals Lf. So Li would be equal to, wait a second. Oh, wait a second, sorry. I messed this up again. So what I said right here, this is angular momentum, so that's actually going to be this, mrv. We just went mr squared here. So again, r is going to be this distance, so 0.5 minus the distance we found to the center of mass, and this would be r. So take the mass times r squared, and that's the answer for 3. Sorry. Okay, then for the last one here, it's going to be I for the whole thing. Which would be this I that we found here. So this I times oh, I'm sorry. This is V. Sorry, V. And times omega final, and solve for that for omega final, and that would be V. VI, translational kinetic energy after the collision. Translational kinetic energy. So that would be 1/2 the mass of the center mass times the velocity of the center mass. So we squared. We found the speed of the center of mass after the collision up here for 2. And the mass would be the entire mass up here. And so plug that in and give us our answer. Rotational energy after. Okay, so V, that's going to be equal to 1/2 I for the whole system. So again, it's this amount here for the whole system, omega squared. Well, this omega here is going to be the final angular speed that we found. Okay, determine the change in kinetic energy as a result of the collision. Well, we just found Oh, I thought, no, I guess we didn't. Well, we know from up here what our initial kinetic energy is. And then we found the rotational after the collision. Right here, we found the rotational after the collision. And we found the translational after the collision. So if we add these two answers together, that would be the final kinetic energy. And the initial, again, would be 1/2 of 0.3 times 4 squared. And so you could figure out the change in kinetic energy.